Hello everyone and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinions and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Saba Balasubramanian, Adam Haig, Ben Wood and Josh Lau, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
So, I think we'll talk about descriptive statistics in a couple of parts. So we'll spend a few minutes today talking about some basic aspects of descriptive statistics. I'll start off with some general comments because the talks so far have been more about epidemiology and research methodology, and we thought we'll give some introduction on statistics. It's really important to get a basic or an elementary understanding of numbers and statistics, I think, for a number of reasons. The two most important reasons are, one is you're reading papers and you're trying to understand scientific data, and you're doing a critical appraisal of these papers so as to get the maximum out of it. And for that, you need to understand some essentials in statistics. The other is, as a number of you people might be doing, is you're designing your projects, you're writing papers on the data that you're collecting, and therefore a good understanding of basic statistics will help you hugely in writing your reports. Why am I talking about it? I've been involved in clinical and epidemiological research for several years now, and I do use statistics to a more or less regular extent, but only basic statistics. I also organize and teach a module on cancer epidemiology for the university, so I think that I might be able to give you some useful information on the basics of statistics. But the caveat is that I'm not a statistician, nor do I have any formal qualifications in statistics, right? So that's really important for me to say. But I hope that if I, as an average surgeon and clinical researcher, are able to give you some insight into statistics, I hope I do that from a very practical perspective, from a perspective that will encourage you guys to also try and understand the elementary principles and start to apply these principles in your own work. Right, the way I see it, for surgeons and trainee surgeons and clinical researchers, there are three aspects or three areas where statistics or biostatistics is important. The first area is relevant to study design. So when you're designing a study, you want to design a study that is appropriate for the clinical question that you have in mind. And when you're deciding on the type of the study, you will use some principles of statistics to help you with the study type and the study design. And if you're doing a randomized controlled trial and you want to ensure that you're adopting the right process of randomization, then again you need some basic statistical principles. If you're in the process of determining how many patients you need for your trial, be it a randomized trial or a non-randomized trial, you need to understand a few basic statistical principles to be able to determine what the right size you should be aiming for. And also, when you're writing a proposal, you should be thinking about what kind of statistical tests you're going to be using when you're coming to analyze your data. So planning your statistical methods a priori is a very key aspect of designing a good study. Okay, the other reason, the other area of statistics that we often use is what we call descriptive statistics. And in descriptive statistics, essentially what you're doing is you are simply describing the data that you've collected. And you might be using things like frequencies and percentages to describe the numbers of patients in different categories. You might be talking about the average or the central tendency, as statisticians call it. You might be wanting to talk about the spread of your data, and you might be wanting to use specific charts and tables and figures to describe your data. Right, and then as you imagine, almost any clinical research paper will have a significant element of descriptive statistics involved. The third area, which tends to become a little bit more complicated, is the use of inferential methods. And essentially, you make use of statistical methods to draw inferences from the data you've collected and you just described. So that's the third area where you'd want to have some knowledge of statistics. Right. So we'll just focus on a little bit of descriptive statistics today. The most important thing that people know about when starting to get involved in statistics is what we call data types. Now, data types are presented and described in many different ways by different people. And often these different ways overlap and are redundant and cause a certain degree of confusion. So I'll try and present the most commonly used ways of categorizing data types, and hopefully this will make some sense. So the first sort of categorization, if you like, is dividing data into categorical data and measurement or scale data. So focusing just on categorical data, what do we mean? So if you're able to put the data value boxes or categories, then that's categorical data. A simple example would be gender. So you've got male and female, so there are two categories, and you categorize all of your patients as male or female. Another example would be, for example, tumor grade. So you might have tumor grades of 1, 2, 3. So you've got three categories, 1, 2, and 3, and you put all of your patients into one of these three categories. Okay, so that's categorical data. Measurement or scale data essentially refers to numerical data. And there are two main types, as you can see on the screen. The first type is what we call discrete data, and the second type is continuous data. Now, discrete data would be things like age in years at the time of diagnosis. So you're looking at completed years since birth. And it could be 60, 62, 70, 75, and so on. And you're not particularly interested in more detail than that. You're not interested if somebody is 70 years, 3 months, and 5 days. You're just interested in the number of years. So that is referred to as discrete data. Another good example in surgical research would be length of stay after surgery. So it could be 5 days, 15 days, 25 days, and you're not really interested in any more statistics like hours and minutes. The other kind of data in the measurement data that is one step further is what we call as continuous data. This is where you get your decimal points and your fractions. A good example would be BMI, and the BMI could be 25.37. And obviously you might want to put some limits on how far down the decimal points you want to go, but essentially the data that is measured on a continuous scale without being limited by the mode of measurement is what we call continuous data. Okay, so I hope that makes sense. We'll look at the next category. So the next category, or the next classification if you like, is qualitative, semi-quantitative, and quantitative. Now you can see that I've boxed qualitative and semi-quantitative under categorical, and quantitative, which is effectively equivalent to measurement or scale. And the reason we are talking about these different classification schemes is because different people use different classification schemes. Different statistical software would call the same kind of data using different terms. Okay, so that's why we're having to revise this. So qualitative data, as I said before, along with semi-quantitative, falls under the umbrella of categorical data. So, and then I've said, I've given you some examples before, like gender, two different sort of sets, male or female. In semi-quantitative data, again, it is in categories, but the categories have a specific order. And quantitative data refers to numbers. Now, the third classification scheme, if you like, is as follows. So you've got nominal data, ordinal data, interval data, and ratio data. Okay, so let's just go through these very briefly. So nominal data is essentially very similar to categorical data. So it falls under the same group, if you like, where you have data in groups, right? Just like I said, gender is a good example of nominal data, or qualitative data, or categorical data. They all mean the same here. And gender is a classic example of binomial data, where there's only two subsets, if you like. They could be data that have a number of different subsets, and that could also be nominal, like, for example, the city of birth. So it could be Sheffield, or York, or Leeds, or Hull. So you've got lots of different cities, and they're all different, they're all separate, and they do not have any specific relationship to each other. So that's nominal data. Ordinal data, on the other hand, is data in categories but have a specific order. A good example would be your Likert scales, where you ask patients or clinicians to agree with a statement, and they'd say, and you can give them choices, and that could range from strongly agree to strongly disagree. Have strongly agree, agree, neutral, disagree, strongly disagree. So that would be a good example of ordinal data, where you know that there is a specific order. Like I said before, grade is a good example of ordinal data as well. So you've got grade 1, grade 2, grade 3. You know that grade 2 is worse than grade 1, and you know that grade 3 is worse than grade 2. Okay? But you've got to keep in mind that the difference between orders does not have a specific meaning. In other words, you don't really know the difference between grade 2 tumor and the grade 1 tumor. You know grade 2 is worse, but you don't really know how worse. And those are the kinds of data types that you would call ordinal. So there is an order in the groups, but the difference really doesn't make a lot of sense. Okay, the next step along this line is what we call interval data. Now, interval and ratio data, I'll explain together. They're both types of measurement data. They're both quantitative, in other words, numerical, right? With interval data, there is a difference between the values, and that difference has a numerical meaning. A good example is temperature. So, for example, you've got temperatures of 0 degrees, 5 degrees, 10 degrees Celsius, let's say, and there's a difference between 0 and 5 degrees Celsius, which is 5, and there's the same difference between 5 and 10. Okay, there's a difference between the values, but the properties of the data set stop there. There isn't an absolute zero, and this is the type of data, interval data, where you don't multiply or divide these numbers. They won't make sense. For example, you look at temperature, there isn't really an absolute zero. Okay, so if you have 0 degrees Celsius, for example, it doesn't mean that there is no, there's absolutely no energy at that state. It doesn't mean that there's absolutely no heat. Okay, so that's what interval data means. And ratio data essentially refers to numerical data where there is a difference between values, and that has a meaning, and the ratio of two values also has a meaning. And this is the kind of data that has an absolute zero. Okay, height, for example, BMI, and so on and so forth. Okay, for all practical purposes, surgeons and surgical researchers could consider interval and ratio data as virtually one and the same thing. And you can use the when you're describing the data sets, when you're using statistical methods, it won't make much sense for you to try and split the data into interval and ratio. You could consider all of this as the same kind of data. All right. So if you're still a little bit confused about these terms, come back and look at them again, and hopefully it'll all make sense. Let's move on. Right. So the other thing you've got to keep in mind is that you take a particular data set, let's say BMI, and you will find that the same data can be either used as a categorical data set. So if you want to call it categorical nominal, then you can simply say that I'll categorize my patients as obese or not obese, and you can have your own cutoff of 20, 25, 30, or whatever you want. You can classify this data as in ordinal data, where you classify them as underweight, normal, overweight, obese, and morbidly obese using your own categories. Or you can use the actual BMI of the patients, use the actual value, and consider this data as a measurement data or a scale data. Okay? And you've got to keep in mind that as much as possible, if you have the raw data, if you have the actual values, do not try and categorize them into, do not put them in boxes. Use the actual value or the raw value as it is in your analysis, and you will find that you get more power in your calculations and your statistical method. If you have absolute numbers, use them. Right, let's carry on. So if you have data that we've called nominal or ordinal data types, such as gender, type of cancer, extent of surgery, and so on, it's fairly straightforward to describe them. So you describe them as frequencies, or percentages, or both, ideally both. So you want to say how many male, how many female, and the percentages, right? So that's pretty straightforward. If you have measurement or scale data, and the examples are here within brackets, you've got your BMI, length of stay, say after surgery, tumor size, if you're looking at a solid tumor, duration of surgery, pain scores, quality of life scores, and so on and so forth. If you're going to describe this data, then you need to use something called the central tendency or the average to say what the middle value is, or what's your data all centering around. And you need to also explain another characteristic called the spread or the dispersion. In other words, say how much your data is scattered or not around the central value. Okay, so to describe your central tendency or average, you probably remember from your high school days, you can use the mean, the median, the mode maybe, but we rarely ever use mode in biomedical research. Okay, so just the mean and the median, and we'll come to that in a minute. And when you're going to talk about spread or dispersion, you've got a number of different parameters: variance, standard deviation, range, and interquartile range. These are the most commonly used ones. Okay, so we'll go through these in the next slide. So, average or central tendency. Mean, we've probably all heard of mean. Essentially, is the sum of all values divided by the number of values. Okay, so that's pretty straightforward. As is median. Median is simply the middle value when you rank all your values from the lowest to the highest, or the highest to the lowest, it doesn't matter, and you go for the middle value, that's your median. Mode, like I said, is the most commonly occurring value and is not really used very often. And when you move on to dispersion or spread, you've got your variance. The variance is what it says here, the average of the square of the difference between each value and the mean. So what you do essentially is you take each value, you subtract the mean from it, you square it, and you do that for every value, and you take the average. So if it's a little bit complicated, you could just Google up variance, and you will find exactly how the variance is calculated. So I won't dwell on it. Standard deviation simply refers to the square root of the variance. So you've got the variance, you just take the square root, you get the standard deviation. Okay. Range is you take the minimum value and the maximum value, and you find the difference. That's range. And interquartile range is simply the difference between the lower quartile and the upper quartile. So the lower quartile is 25th quartile. So if you if you rank your observations from the lowest to the highest, you take the 25th quartile. So you take the median, and then you take the middle value in the lower half of your rankings, and you do the same for the upper quartile. Okay, and the difference between these two quartiles will give the interquartile range. All right. Now, why do we have all of these different measures of averages and dispersion or spread? They have their limitations and their advantages, and I wouldn't go into the details of each of these, but I'll just give you a little summary. And before we go to that summary, I need to talk to you about what we mean by a normal distribution. So you've probably all heard of the normal distribution. There is on your screen a normal distribution of the age at diagnosis of a large cohort of patients with a specific cancer. So what does this show? This simply shows you the frequency, the number of people at various ages. Okay, so as you see on the screen, if you plot a histogram, and that's what this is, a histogram, which is where you take intervals of ages, and here you can see the intervals on the x-axis, 40 to 45, 45 to 50, and so on and so forth, and you plot the number of patients in each interval. Then you have a bar for each interval, and you then take the middle of these bars and you join those dots, and you get what we call the distribution, the frequency distribution. Now, if the frequency distribution is normal, then that's got some important attributes for you to keep in mind. So that's important for you to know if your data set follows a normal distribution or not. Now, normal distribution is also called the Gaussian distribution, or simply a bell-shaped curve. And to call a specific frequency distribution normal, it needs to fulfill certain key properties. The first thing is that there has to be some kind of symmetry, an approximate symmetry at least, around the central value. The central value, or the average, or the central tendency, let's say is around 60. You want to see some symmetry, or the distribution of the data on either side of 60 need to be fairly symmetrical. Okay. The other thing in a normal distribution is that you shouldn't really have any or many extreme values. Okay. And the last point to keep in mind is that if you calculate the mean, median, and mode, they should be very, very similar, if not identical, in a normal distribution. Okay. So these three properties are followed or ticked, then you can say that your continuous or measurement data follows a normal distribution. All right. Okay. Now you can use mean and standard deviation in a normally distributed data set to estimate the frequency or the number of observations within a certain range. So if you take a normally distributed data set, you calculate the mean and the standard deviation, then you should be able to state that 68% of the values lie between mean plus or minus 1 standard deviation, 95% lie between mean plus or minus 2 standard deviation, and 99.7% of values lie between mean plus or minus 3 standard deviation. People to determine or to make an assumption that the data is normal. So people will typically look at the mean, median, and mode. And if they're fairly similar, they might look at how many values lie between mean plus or minus 1 standard deviation. If it's around 65, 68, 69, then they'd be happy. And also look at the histogram. So the histogram looks reasonably normal, then they'd accept that something is normally distributed. Obviously, you can be a bit more picky, and you can say, how can I say for sure? Then there are some statistical tests for normality that you can use, but that's outside the scope of this talk. Right. So going back to how you describe measurement or scale data. So we've talked about normal distribution, and if you remember from a couple of slides ago, we talked about measures of central tendency and measures of dispersion. So for data that follows a normal distribution, remember this, the central tendency parameter that you will use is mean. You should really use the mean. And for dispersion or spread, use the standard deviation. And this is really important, and you find very often in papers don't follow these simple rules, and that just raises a question in the minds of some of the readers, or the readers with knowledge of some basic biostatistics, that if you haven't used the right parameters to describe your data, then maybe you might not have used the right statistical tests either. Okay. For data that does not follow a normal distribution, for central tendency or average, use the median, and for dispersion or spread, use the range or the interquartile range. Okay. If you spend some time thinking about it, using some example data sets, you will see that it makes sense. You will see that if you're using mean, the mean is very sensitive to extreme outliers. So if you have some extreme outliers, very low, very high values, the mean will be altered. But the median is not very sensitive to extreme outliers. Okay, and you know for a fact that in a data that you assume to be normally distributed, you really shouldn't have many extreme outliers. Okay, and in data that does not follow normal distribution, essentially you are simply ranking the observations from lowest to highest and using the middle value as your estimate of the central tendency. I hope that has given you some insight into what kind of parameters to use when you're describing different data types. Right, so we've talked about data types, we've talked about central tendency or average, and dispersion or spread as two ways of describing your data. We've just briefly mentioned what normal distribution is in the context of measurement data or scale data, which could be discrete or continuous, if you remember the data types. And we've talked about what measures to use for normally distributed data and what measures to use for data that is not normally distributed. And I guess in the next talk, we'll look at figures and graphs in describing data.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.